So hello everybody. It's a pleasure to have Tamara here. Thanks a lot for accepting our invitation. Tamara is an astrophysicist at the University of Queensland with over 2 decades experience studying supernovae, black holes and dark energy. She led the dark theme in the Australian Centre of Excellence of All-Scale Astrophysics, and she's currently leading the Australian Dark Energy Survey. Her accolades include the Astronomical Society of Australia's Ellery Lectureship for Career Achievement, the Australian Academy of Sciences Millis Medal for Outstanding Female Scientific Leadership, and member of the Order of Australia. She is an avid communicator of science and occasional guest host of ABC TV's Catalyst, including the episode Black Hole Hunters, which won the American Institute of Physics Science Communication Award. Her TV and movie credits include Stargazing Live, the award-winning documentary Carbon, and playing the voice of an artificial intelligence of living universe. Today, she will present the Dark Energy Survey Supernova Cosmology final results. Tamara, you can start please when you're ready.
Hello, everybody, and thank you very much for having me. Thanks to the organisers for inviting me to give this talk. I'm excited. It's great to be coming to the end of this massive dark energy survey. So I'm very excited to be able to tell you about the results that we've found for the supernova cosmology today. I'm coming to you from the lands of the Turrbal and Yagara people here in Australia, in Brisbane. So I pay my respects to the Aboriginal elders, past, present, and emerging here. There's a great tradition of astronomy amongst the local people from Australia, and including the stories of things like the emu across the sky in the Milky Way galaxy, which we have a great view of from the Southern Hemisphere. So, dark energy survey, this little animation that's been going on in the background, sort of trying to hypnotize you while you're gathered here, is a little animation of some of the supernovae that we saw go off in these 4 narrow cones that we searched for 5 years for supernovae. I started this project in 2012, and that was when we got our first test observations with the Anglo-Australian telescope, getting spectra of the supernovae that DES had found. And many people had started this project earlier than me to design and build the telescope camera and experiment. And so there'll be, what I'm hoping to do today is show you the results, but also give a lot of credit to all of the people who have gone into making this amazing data set and doing the analysis, particularly some of the early researchers. Okay, so where are we going? So starting way back in the deep dark depths of history here for cosmology, we have the first Hubble diagram, a measurement of velocity versus distance. This image is the one as published by Hubble. Of course, Lemaitre had the one in 1927. And this plot here has 24 nebula distances, so using things like Cepheids and but also some other measurements. So this was some evidence that the universe was expanding. And I love this quote from the paper from Hubble: "For such scanty material so poorly distributed, the results are fairly definite." I like the little self-deprecating quote there. In the late 1990s, of course, there was this Hubble diagram. We use different axes now, more directly what we measure, which is the distance modulus, the difference between apparent and absolute magnitude, and redshift, and this was made by 2 different teams who between them measured that the expansion of the universe is speeding up. And these between them had 52 high redshift supernovae, and you can see some of them getting a Nobel Prize here, and the group photo that I could find of the others over here, and that was a pretty cool achievement. So we now have a new Hubble diagram. A couple of decades later, you'd hope we were doing a little bit better. And what DES has contributed is 1,600-ish high redshift supernovae, and we have 4 different colors that we've measured, so 4 photometric bands. And this is the Hubble diagram that we have here. And down here are some of the people that have contributed. This is some of the Supernova working group in particular, many of whom had a major role in the supernova part of this analysis. And this new Hubble diagram has on it 80% of the known high redshift supernova 1A. So by known, I put a little asterisk on that because we know of many more. In our own sample, we have thousands more. But these are the ones that are super high quality, really well, like just perfectly like normal type 1a supernovae, no peculiarities going on, and are on the Hubble diagram. So this is by high redshift, I mean above redshift 0.5. Cool. So how do you do supernova cosmology? Quick outline. I'm sure many people here are familiar, but just to make it abundantly clear, we have the theory of how luminosity distances of supernovae relate, also the distance modulus, which is the thing that we're measuring, so basically how bright they are, relates to how far they are away. And this depends on cosmological parameters according to this integral over basically how Hubble's constant changes with redshift, which is given by these different equations in a few different models. So these were the models that we tested for in the Dark Energy Survey key paper. The observation is an observation of how bright the supernova is in a particular, it's not actually necessarily in B band, it's in just a cumulative sort of band. And how bright each supernova is not just a standard candle. It's because they do vary in brightness quite a bit. It's a standardizable candle. So the brightness depends on a few different features of each of the supernova, including how wide their light curves are, what color they are, some properties of their host galaxy, and bias, a calculation of the bias due to selection effects. Then there's a few population parameters that go for the entire supernova population, and this is just how supernova behave as a function of their stretch, color, host properties, etc. So those are common to the entire population. And so it's comparing these two mu's that gives us our cosmological fit. And here's just an example that Anais Moller made from some of our data showing before doing any calibration to the supernovae, how much scatter you see in the peak magnitude. And then this is an example of just using the first two corrections, how much neater the data can get. Okay, here's a little bit on the theory side, a little bit more detail. Of course, you've got to put a couple of proper details in these equations. Luminosity distances require two different redshifts because the bit that does the beaming and the time dilation needs to be the observed redshift, but the bit that goes in the integral has to be the cosmological redshift. We also have to take into account curvature if our model's not flat, and that sort of thing. So, but those are just some details we don't have to worry about too much. Okay, so what does our data actually look like? Here is a plot of all of our light curves, which it's surprising sometimes how rarely you look at the actual like raw data of what you're talking about. And this is just sort of in arbitrary units, so which is why I haven't put the scales on here. It's more just a pretty plot, but you can see how dramatically different the fluxes are in the nearby ones, which are really bright, and the faint ones, which are down the bottom. And so the red here is low redshift and the yellow is high redshift. And after you've done the characterization by the distance modulus equation I just showed, this is more what the light curves look like. So this is what we're using essentially as a standard candle. And you can see here some of the rough correlations between stretch and color that we correct for. We have a little a wall in our department that we put accidental art when we put up a plot. So I put this in the running for our year's accidental art thing because I thought this was actually quite pretty. And if you were not noticing that the title of my slide was actually just the zoomed in bit of the light curves from the Dark Energy Survey so far. Okay, so what am I going to cover in this talk really? I've given a bit of general intro on supernova cosmology, but for the Dark Energy Survey specifically, I'm going to let you know how we measured the data, how we made the Hubble diagram, give our results, and have a bit of a look into the future. This is the camera of the Dark Energy camera and the lens that makes it work. Okay, so Dark Energy Survey. This is a picture from DECCAM. It's an absolutely phenomenal camera down on the telescope, the Blanco 4-meter telescope in Chile. Its field of view relative to the size of the moon is about yay big, so you can see big patches of the sky at once. The resolution is also amazing, so if you zoom in on any particular tile, you can see something like this, so you get this incredible view of big patches of the sky in great detail. We did a survey that covers this patch of the universe. It's about an eighth of the night sky, and it's affectionately known as the tank for good reason. But it was chosen to miss the galaxy and go along commonly viewed regions like stripe across the middle is stripe 82. The supernova survey was a small part of the total observing, in that the whole big area was surveyed over the course of 6 years. But for 5 years, we repeatedly went back and looked at these little circles. So these 10 fields, 2 of which we looked for longer than the other 8 to get slightly deeper. And these are the fields in which we were discovering supernovae. We had a cadence of about observing every week approximately during the season that our fields were visible. And so this is a picture of the cadence for our different fields for one of the years. And we deliberately chose regions of the sky that had low Milky Way extinction. And in there, we found things that look like this. If you zoom in and you zoom in and you zoom in again, you can see one of the really nearby supernovae that was a really obvious one that showed up in one of our fields. So this is one of the lowest redshift supernovae in our sample. This is not a type 1a, it's just a pretty picture. Most of the ones we're looking at are in the tiny dots in the greater distance. So this was another animation of basically what I showed before of discovery of the different supernovae over time. And we did this, you can see these, we had to distinguish all the things that vary in the sky and pick out the supernovae amongst them. Now, finding the supernovae isn't enough, because to put them on a Hubble diagram, we need to know their redshifts as well. And that's why we started OSDES. So Chris Lidman was sort of the heart and soul of OSDES at the beginning, and he helped get this off the ground. And this circle here is the field of view of the Anglo-Australian telescope superimposed on the field of view of DECCAN. Anglo-Australian telescope has 2DF, which is the 2-degree field instrument. It's a 400 fiber spectrograph, and we put the fibers on interesting objects in the field, about 100 supernovae each time we went back to each field, but also active galactic nuclei and anything else of interest that we were monitoring. So what does 2DF look like? Hopefully this animation works properly. You can see this is the robot that puts the fibers in place on the pointy end of the 4-meter telescope, and this is what we used to target many objects at a time, which made our follow-up efficient. Now, importantly, to do this, we weren't taking spectra of the Soviet belts. We were taking spectra of their host galaxies. Some of the supernovae in our fields were still live and bright when you took the spectra, so there's supernova spectra in there. But the majority of the redshifts we got for this project were all from the host galaxy, the galaxy that hosted the supernova, not the supernova itself. We want that because the host galaxy lines are sharp and they give you a better redshift than the broad supernova lines, and also because it gives you a simpler selection effect, selection sample. So you don't have to worry about whether you got a spectrum of the supernova when it was live. It gives you an easier analysis as well. This is not a supernova spectrum. I should put a supernova spectrum in here, but this is just an example of the kind of actual data that you get. This is an AGN at higher redshift. So anyway, yep, that's how we discovered these supernovae and put them in terms of redshift distance on this plot, on this animation. But what do we then do with the data? So we've known for a long time that for supernova cosmology, systematic error control is going to be key. So it's for the last decade or so, most of the supernova cosmology analyses had already been hitting the systematics floor, where were uncertain enough about some aspect of the analysis, be it calibration or contamination or anything, that the estimated size of the systematic uncertainty was equal to or larger than the size of the statistical uncertainty. And of course, if that is true, then there's no use getting more data, because more data doesn't let you reduce your error bars. So the key thing, the whole part of this analysis was Des was built from the ground up to get really good data so that we could control our systematic uncertainties and reduce that systematic error budget as much as possible. So I should point out that these is our 3-year sample, which was spectroscopically classified. So these were ones that we had spectra of the supernovae themselves. That one, we found that the systematic errors were equal to the statistics. So this is our sort of error budget of our 3-year sample, where the systematic and statistic were actually exactly the same. So how did we do better? I'll get to more of that, but this is our final error budget. The systematics is less than half of what it was, and now is significantly lower than the statistical error budget. So this was a major success of the whole effort, and this is basically where all the effort went into. And so let me explain to you how some of this actually was achieved. Okay, so firstly, I've already mentioned one of the differences between our analysis and some previous ones. We had about 20,000 potential candidates, and we didn't get spectra for all of them while the supernova was live. So we did photometric classification of these supernovae. We used 3 different types of measurements. These were different machine learning efforts to do the classification. But it turns out that not much looks like a type 1a except for type 1as. Type 2 masquerade as type 1a sometimes, but even just the basic fitting, if your light curve fitting works, you've already cut down most of the contamination in the sample. And these machine learning efforts helped to get that refining bit at the end. And after all of the effort for doing this classification, the photometric classification part of it really ended up not being an issue at all. There's about 3% contamination in the sample, and that doesn't have any significant impact on our cosmological results. It's less than 10% of our systematic error budget. So very, very happy with this. That's important because it helps things for like LSST and stuff later. Oh yeah, and just to point out again that even though we don't have spectra of the supernova, we do have spectroscopic redshifts of all these. There is another effort to do photometric redshifts as well and do cosmology with that, but we haven't done that. So this is all still spectroscopic redshifts. Another important thing is modeling the intrinsic scatter. Now I'm going to go lightning fast through a bunch of these things so I can get to the cosmology results. But I have to, a bunch of these things are like multiple PhDs that I'm going to cut through in 30 seconds each. So apologies to the wonderful PhD students and postdocs who have done all of these analyses that I'm going to summarize so quickly, but it was Herculean efforts for some of them. So I appreciate all of those massive efforts. So when you're looking at the scatter in supernovae, we calculate our uncertainties. There's about 10% unexplained scatter, which we expect is intrinsic diversity in type 1a supernovae. We know that they're not going to be perfect objects, so that's fine. And there's also been a lot of discussion about the offsets due to host galaxy properties and how they relate to different things. Like here we show a couple of different splits of looking at host color as opposed to host galaxy mass, and how the dust is modeled. And we've used a couple of different methods here and used the differences between the methods as an estimate of some magnitude of this possible systematic in this particular part of it. We did a deep dive into the host galaxy associations because sometimes we're going to think the supernova is in one galaxy, but it was actually in another. And Helen did an amazing job of looking at this in great detail, and this also has a small effect on our total error budget. We account for atmospheric effects. So Jason and Maria did some great job here where different colors get diffracted through the atmosphere differently. So when you're looking at where your supernova has landed on the chip, you have to take this into account. Otherwise, you get your photometry wrong as a function of color. And this has not often been taken into account before, but we did this, and that's how we got down to some of the really amazing photometry that we had. Another one that we looked at in detail was how we do the get the magnitudes of the supernovae. So the difference between, you have to subtract the host galaxy light. Often you do that with different imaging. but we did full forwards modeling of every host galaxy so that we could subtract the galaxy more accurately with different seeing conditions and all of that sort of stuff. So Dylan was a hero on doing that analysis. And many people, including Georgie Taylor, looked at the light curve modeling, and there's a new SALT-3 model that Darcy also contributed to that gives us a new, better calibration of the light curves and our measurements of their peak brightness. So diving straight through even more, there's more. This is the steak knives show. I don't know if you know that joke, but there's always a little bit more. So we also looked at how you do the actual cosmology analysis. We used to do redshift binning. We don't do redshift binning anymore for fitting cosmology. Previously, it was done so that you could do bias corrections and stuff in bins of similar supernovae, but that we find that loses a lot of information. And so avoiding doing any binning in the cosmology fitting is a good way to get more out of your data. And of course, we then also did some important double checks of the cosmology analysis. Patrick Armstrong looked at validating the size of the uncertainties that we were because some of our the population about the scatter about the Hubble diagram and things aren't necessarily always Gaussian. So you need to make sure that what you're quoting as your error bars are valid. And we found that worked really nicely. And Ryan Camilleri also looked at a really important question of the how cosmology independent our analysis is. So the place where cosmology dependence might enter is when, for example, we did lots of simulations of our survey so that we could calculate selection effects and validate our analysis. And if any of those simulations, because you have to assume a cosmology when you're making a simulation, if the simulation cosmology affected your output cosmology at all, that would be. So we made sure that wasn't an issue, and Ryan did a beautiful, convincing job of that. This plot that you're looking at is the equation of state of dark energy versus matter density. The true cosmology in a simulation is the dashed lines, and if your simulation cosmology was exactly true, you ended up with a result over here. This is just a single realization, so you don't expect it to be perfect. But then if you tried lots of different reference cosmologies, even being 10 sigma away from your final answer, you always end up comfortably within this 1 sigma contour with negligible changes. So that was really reassuring. And this is going to come out in a paper very soon, hopefully. And you can see the amount of change in distance modulus that the reference cosmology can have. That can have a very small change in the output cosmology is extremely reassuring. I also mentioned that we would I have a new parameter for you, and I forgot to put the equation in. Damn it! I'll have to drag that out. But basically, there is a degeneracy direction that goes through this this W omega m degeneracy, which is basically in the cosmographic expansion. It's actually little q, like the deceleration parameter, times h squared, which is why we called it QH. And it can be calculated at different redshifts. And you can get rid of this degeneracy and quote the main result of the paper in just one parameter. And this can be a useful way to summarize results if you just want to not worry quite so much about this sort of massive degeneracy that you see. It's a bit in analogy to S8 that's used for lensing studies. And you can see that here, when you have this big degeneracy, it can look like the answer for W or omega m is changing a lot, when it's actually not a very significant change in terms of the error contour. And so you can find your changes in omega m can look dramatic when it's actually just sliding through this degeneracy direction, and QH gets rid of all of that. So it can be a potentially handy parameter to use. Okay. Sorry if I'm going a little bit fast. I promise I'll get to the results soon. But bringing it all together was this pipeline that was written by Sam Hinton, which is called Pippin. And Patrick Armstrong has been maintaining that since Sam left us and went into industry. And it was bringing all of these things so that you could push one button and all of these previous steps all essentially happened automatically. So that was great. Now, Maria and Dylan were the heads of the leads of the cosmology analysis, and Maria was our systematic error budget guru, and so she was the one that was looking at making these beautiful plots of how big our systematic uncertainty is compared to our statistical. And it turns out that one of our smaller systematics is classification, as I mentioned before. The top systematics that we have to worry about and will be important for future supernova surveys is calibration, so training and fitting the supernovae, and the host dust, the host galaxy properties and the dust properties. So this is important to be able to help identify the critical path for future surveys that are being planned. The results, as promised. So here is the papers that are the supporting papers that are mostly published that contain all the results that I was just talking about. So what I'm going to show you now is the results that build on all of these various papers. This is the histogram of the sample that we use on our Hubble diagram. So the blue, the new high redshift sample that Dark Energy Survey has contributed. You can see this massive spike that increases the number of useful supernovae out at very high redshift, which is the really big different contribution from this sample. One of the things that we did that was really important was we just concentrated on using really, really high quality data that reduced our possibilities of systematic uncertainties. And that means we actually threw out a lot of the existing low redshift sample because we couldn't calibrate it as well as the rest. So we chose only those that we had really good calibration for. We could have much better statistical uncertainties if we had included some of these. So our R's been smaller, but we discarded more than 2/3 of the existing low redshift sample in order to preserve the high quality of the calibration. This is, I think, the favorite plot that I wrote in a paper. I thought it was just really quite pretty. But these are our light curves in 4 different bands. And looking at this, you can see an important feature in that as the supernovae go up in redshift, so vertically here, these are offset by redshift, just arbitrarily offset in height. And we lose the G band at about a redshift just under 0.4, and we lose the R band at a redshift about 0.85. So for the very high redshift ones, we only have 2 bands. We combined this data with baryon acoustic oscillations from SDSS, with cosmic microwave background data from Planck, and by 3x2 point also from the Dark Energy Survey. So the 3x2 point is the most obscure probably of these measurements. So just to explain what that is briefly, when you're looking out at distant galaxies, you see they're lensed by foreground clusters. And what you can do is you get the 2-point correlation of the galaxies in the foreground. You get the cross correlation between the galaxies and the lenses in the background, and you get the correlation of the lenses themselves. And you do all of these simultaneously, and that's your 3 2-point correlations that you fit. So that's another of the major streams of the Dark Energy Survey that had already published results. So we chucked them in our sample as well. Okay, here is us and our unblinding teleconference. We had an exciting time. It was actually very tense. I was like really nervous as this was happening. This is like over a decade of work for me, so to see how it comes out was a little bit stressful. Of course, we did this all blinded so that we weren't biased by the cosmology results that we were seeing as we were preparing the analysis, which is an important thing for all cosmology these days. And here's us just after the unblinding, looking happy and excited and maybe a little bit relieved. Okay, so what did we find? So this is our plot for the likelihoods for flat lambda CDM. And you can see a bunch of different curves here. The ones for our sample alone, which is 194 low redshift ones plus the new high redshift DES ones that we added, is this light blue or cyan sort of color one over here. And then once you add C and B to that, you get the blue contour. CMB alone is the black. When you add BAO plus 3 pi 2 point, you get the light orange one here, and the redder one is when you put them all together. Now, something that everybody pretty much notices is that, weirdly, the one where you put them all together is to the left of the other contours that are all over here, or the other likelihood distributions, which are all over here to the right. So why does that occur? Well, when you add another parameter and allow for curvature, you can see why this occurs. So here now in lambda CDM, you see the cosmological constant density and the matter density here. And you can see same colors, the supernova from DES have this slant to the right. CMB has the slant to the left. When you have the BAO and 3 by 2 point, it's sort of in the middle here. And you can see that where those contours cross, it's sort of to the top left of the flat universe line. So if you are constraining to flatness, your matter density would be on the left of any of the other individual measurements together. So that's why this peak here on the flat lambda CDM one is to the left for the combined, then all of them separately. So that's just an interesting feature. We see no evidence at all that the universe needs to be curved. The flat universe works is a really good fit to our data. And now you might notice that this plot on the right with the DES supernovae looks very similar to this original supernova data plot. This was the two teams that were prior. And it does look very similar. Indeed, it looks like that. That's the difference. But it's important to, of course, remember to look at the axes. And if you zoom in, that's what our plot now looks like compared to the original data. So even though it looks similar, some progress has been made in the last 25 years. Okay, now, is the equation of state of dark energy -1, is it a cosmological constant or not? That's one of the simplest things that everybody wants to ask. And this is the plot that we found for the WCDM model, where we test the equation of state of dark energy. And you can see the cyan contour, which is the supernova, tends to be a little bit above this. And so when you combine it with the CMB and the others, we end up with the answer being that W is slightly less negative than -1, so slightly more positive there. And where it's not very significant though. Like this is like only a couple of sigma away, even for the combined contours. So it's possible that this is a statistical fluctuation upwards. But one of the things that the reason that we wanted to go to high redshift and get this big new sample is because we want to know whether dark energy is time varying. And having a W equals -1 having an equation of state that is constant but not equal to -1 is a very unnatural model. If it's not -1, it's probably time varying. And so we looked for that as well. And we found that there is a preference for time varying dark energy in our supernova data. Again, not massively significant. There's a lot of degeneracy here and reasonably big error bars in this plane. But this is the tightest constraints that a supernova survey has in this model. And so it's quite interesting to see. So we're not reading too much into that yet, but it does motivate looking for future samples and other types of measurements in this area as well. You can see what the different models look like here. So this is actually looking at what the best fit time evolution looks like. So the green is the time varying flat W0 WA model, and then the pink is the best fit flat lambda CDM compared to the Planck one, which is the dashed blue one there. So you can see how they sort of differ on this kind of Hubble diagram plot. And here's our boring table of numbers, which you can would say yes. It's actually a surprisingly subtle thing to try to answer. Even fitting a cosmographic model where you have your deceleration parameter Q naught and jerk and stuff, it depends on how many orders you go up to in that to determine this. So we're looking at Q naught defined as in lambda CDM. We find very strong evidence that Q naught is less than 0. We actually find, because we're looking further away, we're actually even more confident that the universe was accelerating at redshift 0.2 than we are that it's accelerating now. But once you add flatness as well, there's essentially no part of the likelihood that is not accelerating. Next one is dark energy, a cosmological constant. Maybe. We found maybe it's not the best fit, but there's no strong evidence against the cosmological constant. These are what our best fits would look like on a time varying dark energy, just to show you in this linear dark energy changing model what would actually happen. So as a function of scale factor, the equation of state of dark energy would be increasing over scale factor. There's one detail I forgot to mention when I was looking at this one, actually, but now I've forgotten what it was again. I'll come back to it if I remember. Oh, it was that you actually can get away within our uncertainties having no constant dark energy and purely time varying dark energy. Anyway, that's a relatively unlikely model. But interestingly, I also wanted to mention this other supernova analysis that came out just before ours in December. And this is the Union supernova team. And they had a different philosophy to us. They used archival data that included as much data as possible, rather than trimming down to find only the best quality stuff. They did an absolutely amazing job of doing the calibration for all of this other data that exists out there in the literature. And interestingly, they're finding a similar result to us, with W a little bit high, and their time varying equation of state 1 is in a very, very similar region to ours, a bit below what you would expect for the standard cosmological model. Pantheon Plus previously did not find a massive difference there. Okay, how old is the universe? If our results are true, it's a little bit younger than we thought. It would be, and this is actually an important detail, because we do remember that one of the things that the supernovae solved in the 1990s was the universe used to be younger than the age of the oldest stars, if you calculate the age of the universe in a purely decelerating sense. So when you look at our data, our best fit in WACDM would be almost 10% younger than the Planck cosmology, and that probably does have issues with the age of the oldest stars. So in future analyses, we could use that potentially as a prior to say that it has to be above that region. Yeah, so you can look at that. Finally, does our best fit resolve the Hubble tension? No, unfortunately. In these simple models, at least, the only simple solution for these ones would be that resolves the Hubble tension would be W less than -1, and we're finding it sort of the other way around. But also really important to note that we do not contribute a new measurement of H0 with this data. We only have high redshift supernovae that we've added new, and so we don't add anything to the H0 debate in terms of what the value is with supernovae and other measurements at low redshift. We only have contribute to how the time evolution of the universe might have changed from the Planck to now, or from CMB to now. Cool. I think I'll skip over because I'm running out of time. These. Okay, so getting to the wrap-up point, what are we doing for the future? Obviously, we're going to make our data public. That's imminent. We have the referee report back, and so it's looking good. So hopefully that should be very, very soon now. We want to combine with more data sets. A really, really cool thing would be more low redshift data. So ZTF, DBAS, some other things. The DBAS group are doing low redshift supernovae with DECAM. So that would be great because everything will be calibrated on the same system. So we don't have to worry about any cross calibration or anything like that. So that could be super, super useful. We still have a lot of dead supernovae that we didn't use on here. We think that there's over 1,000 type 1As that still need redshifts at high redshift. So we can still do that, some of that. And what I'm probably most excited about are some of these other analyses that are being done. So we're looking at lensing of the supernovae. So they should be magnified or demagnified depending on how dense their line of sight is. We're testing a whole suite of different cosmological models, more exotic models for dark energy and things. And so Paul's leading the supernova lensing, Ryan's leading the other models. Another Ryan is, who may be on this call, I think, is doing a measurement of time dilation, which I'll give you a sneak preview of in a second, because I think that's sort of fun. And we're also looking at doing inverse distance ladder, so using baryon acoustic oscillations to calibrate the supernovae, and also supernova physics and cool, interesting objects in our data set, which we still need to find. And it's there's going to help the question what is what are the laws of gravity, and those can be super powerful and complementary to supernovae. If I have time, I can give you just a quick flash of one of the DESI predictions, but in the interest of time, I'll give you this very, very quick sneak peek here of Ryan's work looking at time dilation of supernovae. This is just a measure, and it's preliminary. We're still working on some details of the uncertainty measurements and things like that, but this is basically how wide the light curves are as a function of redshift. And if they go as predicted, you get time dilation which is a function of 1 plus z, so multiplied by 1 plus z. You would get the dotted line here. And the best fit to our data at the moment is the blue dashed line. So that's on its way. It's a really nice demonstration that, yes, the universe does appear to be expanding. Our redshifts are due to galaxies moving away from us. Yeah, and I think it would be just really cool to quickly mention the baryon acoustic oscillation measurements that are being made by surveys like the Dark Energy Spectroscopic Instrument, who've already released 2 million objects. Doing the same thing that I did for the supernova on this little zoom-in plot that we had before. This is the prediction for what baryon acoustic oscillation should be able to do in the cosmological constant versus matter density plane. This little pink thing in the middle, which if you zoom in, looks like that. If you have trouble seeing it in the middle of there, it's because it really is extremely small. So it's, as always, having many different complementary measurements of the same thing is going to help us be confident in the robustness of our results, regardless of what different systematics are plaguing different analyses. Okay, so I'll leave it at that. Thank you very much for listening, and I'm very happy to answer any questions that people may have.
Thanks a lot. Thanks a lot for the very nice talk. Are there any questions? Thomas?
Well, Tamara, thanks a lot. I'm still hypnotized, and that's why I would like to have more information on your lighthouse, please.
On the lighthouse, did you say?
The lighthouse, yes. That you showed in the beginning and a few other flashes later.
Yes. I may have sped through this a bit too quickly. So what you're looking at here is we're at the center of this, looking outwards. These 4 different stripes that you can see are the 4 directions that we looked out with the Dark Energy Survey. So if you recall this plot here, these little dots here, there's 10 fields, but they're gathered in 4 different directions in space. And so the video that I'm showing here is every golden dot is a galaxy that's in those directions, and all the sparkles that you see going off, those are the supernovae going off. and they're timed such that they fade at the correct times for when they went off. And this is 3 years of data. This is the first 3 sped up and fast forwarded, and the rotation is just for fun to make it look good. So the sparkles are the supernovae going off. Just to give you a sense of scale as well, you can see that the density of points drops off about sort of halfway. You can see it's sort of like, I don't know if you can see my mouse very well, but there's the density of golden points drops off. That's a redshift of 1. And that's because that's when the O2 doublet moves out of the red end of our spectrograph, and we struggle to get emission line galaxies after that. So that's why that density drops off. Most of the dots beyond there are AGN. Is that what you're looking for?
Absolutely. Thanks a lot.
Thank you. Erin?
Hey, Tamara, thanks for the talk. It's interesting. I have a couple of comments and then a question, right? So it's interesting that you find that like the CPL model has a problem with the age of the universe, right? But that's not like, where I want you to go with this. The CPL model itself is more a diagnostic of lambda. You know, basically, there's nothing to stop me assuming the matter is pressureless, and then I reconstruct a function that's the dark energy, density. And that can be a complete function. It can have an infinite number of degrees of freedom. There is essentially no physics in doing that. So in some sense, what WCDM and CPL are diagnostics that it's not lambda. So it's not the cosmological constant. Now, so if we go back to lambda CDM, the physics that you have in it is you've got the cosmological constant, you've got pressureless matter, right? Now, in some sense, what you're saying in these results is that it's maybe not the cosmological constant, okay? But we can also test this the other way around. We can basically get rid of WCDM, we can get rid of the CPL model, and we can take the lambda CDM model and just bin it by redshift. Myself and Shaheen have been doing this. And this then would relate to H0 tension, because what H0 tension tells you is that one of your fitting parameters, which you assume is a constant in your model, in your lambda CDM model, that's not a constant. If there's no systematics, that's what it's telling you. Now, the other constants then you need to look at. Now, if we do a consistency test of the lambda CDM model, look at fitting parameters at all redshifts, and we find that the fitting parameters never evolve or never change, that says that there's no real problem with the model. So getting back to the DES result, what you seem to be finding is that in your flat lambda CDM model, you're sensitive to omega m. This is essentially the only parameter you look at. You have a sample with a high effective redshift, and you find that omega m is a larger value, and it's like 2 sigma away from Planck. Okay, myself and Shaheen have been doing these tests since 2022, where we've been looking at supernovae samples, quasar samples, observational Hubble data, and we have been deliberately changing the effective redshift of the sample, right? And what we find is omega m increases. The fitting parameter actually changes with effective redshift, and it's consistent with your results in DES. Do you have any comments on that?
Yeah, so what we're seeing
like the first point is basically that the CPL is a diagnostic. It's nothing more than that. And the fact that you find it's inconsistent with the age of the universe would just tell us it's a bad model. And then whether or not we can actually do these tests in lambda CDM itself.
Yeah.
And show
so just so everybody's on the same
model.
page, CPL is this one that's on the right here. It's the WA CDM one. And so it's just a linear variation in the equation of state of dark energy. So as you say, there's no great physical motivation for that. It's just looking for, is there any indication that some sort of time variation, let's just try a linear one, is better than no time variation at all. And so in that sense, yes, I'm in agreement that what we're seeing here is that maybe there's a hint that, as you've been saying, there's that the simplest model with a constant dark energy is not the best one. It's not so dramatic that I want to like say this is a massive new discovery or anything like that we're sure of anything yet. But
just
it's
Tamara,
intriguing.
if I can, just very quickly, like if we just study lambda CDM and we find evolution in omega m, the fitting parameter, I can only say it's either a problem in dark energy or it's a problem in pressureless matter. I can't separate those two. Whereas if you find evolution in the dark energy sector, you can say it's not lambda. But you've still hardwired in the fact that it's pressureless matter in the CPL model. You've built that in by hand, right?
Yeah, so the paper that Ryan Camilleri is doing is going to look at a whole bunch of more interesting parameterizations, some of which are more physically motivated. Yeah, thanks.
Thank you.
Thanks.
Alain?
Hello, thank you for this nice talk. I was wondering whether there is a plan to combine the DES result with the Pantheon result to get a more accurate constraint.
Yeah, that would be awesome to do. So we want to add include many of those data sets together. And so I think there's value in doing a variety of different things. So as I said before, we cut out some of the stuff that's in Pantheon because we didn't think it was high enough quality to include for our analysis. We wanted to be just as beautiful and pure as possible. But there is also the philosophy of chucking everything in the bucket, a bit like what the union team do. And that can have advantages as well, because sometimes, maybe there is a subtle systematic in there. And if you have a few different calibrations, sometimes some will be systematically up, some will be systematically down. So maybe that actually even helps by canceling things out. But what I'm actually most excited about is some of the new samples that are coming up. So ZTF has thousands of low redshift supernovae. It's a beautiful, beautiful survey, which I think would be fantastic to include with the high redshift stuff from DES, because those are really complementary. And having supernovae calibrated on the same instrument is also very valuable for systematics control. So number one thing that we want to do is, now that we've got this out, let's throw the kitchen sink at it and combine it with as much stuff as we can and see what we find.
Thank you.
Yeah.
Thank you. Giuseppe?
Hello, thank you for the presentation. I had a more operative question. So if once the data will be out, would it be possible to use, I understood that you do not measure H0 directly, but if the data, once they are out, it could be possible to use them to, I don't know, use a cosmological model to derive an estimate of H0 if once one has to do calibrations, I don't know, or something like this. So
yes, the reason that we make no attempt to add to the measurements of H0 is because our lowest redshift ones are basically start at redshift of 0.3. And by the time you get out to redshift of 0.3, there's enough cosmological model uncertainty that you're not really directly measuring H0. You're not measuring H at the present day. So the kind of thing that we can do is things like this inverse distance ladder, which is a slightly different one, where you use BAO to calibrate your supernovae at high redshift, and then see what that implies for H0 at low redshift. But yeah, the fact that we only have a new high redshift sample and all of the low redshift ones have already been used to measure H0 is the reason that we're not attempting to contribute more to that discussion with this data set.
Okay, but could be possible to use as an anchor, I don't know, other supernova sets which are more linked to a low redshift range. So it's like adding a middle step in the cosmological ladder, or?
Sort of. I don't think it's going to directly help H0, but the one thing that it can do is help with the calibration of the supernovae themselves. So the diversity of the supernova population can be better understood now that we have thousands of them. And so one of the reasons that I didn't really emphasize the systematic control was improved is because now we have so many supernovae, we're able to better characterize how they behave. And with really clean data, so that it can help in that sense. Yeah.
Okay, thank you.
Thank you. Vivian?
Hello, thank you very much for the amazing talk. It was really, really nice. I was just curious about the compatibility, whether you have any test to test the compatibility with the BAO result, and whether it's okay to just combine them. Because if we're being a bit, aggressive in how we use the BAO, combining, for instance, with Planck as another sound horizon-based measurement of the late time expansion history, the values of omega m, even under flat lambda CDM, tend to be closer to 0.3 than 0.35. I don't know what would happen in the CPL. I don't know whether even in the CPL case, things are even worse in terms of compatibility. Have you looked in that at all? And the connected question is, to what extent part of what we're seeing could be volume effect because you're only selected, the high redshift of the supernovae. I mean, higher redshift of the supernovae, hence maybe closer to a matter-dominated universe than a dark energy-dominated universe. I don't know whether there's any impact in biasing a little. I don't know if it's a bias of sorts, but just changing a bit the value of omega.
Yeah. So the first part of your question was
compatibility with BAO. Yeah.
Oh yes, compatibility. I was like, gotta try and remember. So compatibility with BAO. So when we looked at these, so it's important to note when you're combining data sets whether those data sets are consistent enough with each other that you can combine them, because the classic thing is have a contour way over here, a contour over here. They overlap in some tiny little corner, and you have really tight constraints, which are just indication of a bad fit to the data. So we did all the statistical tests on these, things like the suspiciousness statistic to see whether these two data sets were compatible and allowed to be combined. And the answer was yes for everything. So it should be, they do sometimes pull each other different ways. Like you can see like the CMB and the supernovae, the CMB 1 sigma contour doesn't quite touch the supernova ones. But they're not so far in tension that that's something that we had to worry about. So we did look at that carefully. In terms of the looking back into the matter-dominated universe, it's actually one of what the supernova do to test the all of these different parameters is look at how the universe was different in the past compared to now. So when we're looking at these Hubble diagrams, the absolute calibration of the supernovae doesn't matter. So on this sort of double diagram, it doesn't matter where vertically these supernovae are. What matters is the slope as a function of redshift and how that slope changes subtly. It looks straight on this plot, but it does have a curvature. And so it's the difference in curvatures between high redshift and low redshift that gives you your constraining power. So you really want to be going back into the matter-dominated regime and seeing how the distance redshift relation is working back there compared to how it's working now. And that actually is what gives you your constraining power that lets you differentiate matter density changes and dark energy changes.
Yeah. So that's my point in a sense. That is, since my understanding is you're adding a lot of data in the round. I mean, I don't know if you consider that high redshift, but 0.3 and above.
Yeah. That's what we're calling that high redshift.
Pool?
Everybody.
Yeah. Anyway.
Yeah.
So anyway, yeah. So okay, I understand.
Yeah.
So Vivian, I think if you basically balance this up with a lot more low redshift supernova, you would get different results. You'd get omega M pulled back towards 0.3. So
this is what.
So this is poorly anchored data at low redshift. That's what DES is. It has a high effective redshift.
It does.
It needs to be tested though, Tamara. That needs to be tested.
Yeah. So that's exactly the reason we want to combine with lots of low redshift data and that sort of thing. This is still well anchored. 200 supernovae at low redshift is still a lovely sample, but
the effective redshift of the sample is very high, Tamara, right? So
agreed.
My worry is that it's not everything's being skewed by the high redshift supernovae. So if you combine this with Pantheon Plus, for example, then we'd have a whole load of, we have 700 supernovae below 0.1. That would provide much better anchoring, right? And I think you'll get a lower value for omega M.
Yeah, so the only thing I'm contesting about any of that is whether it will change the answer or not. And so we'll have to do that to actually test. But it's perfectly possible that add more supernovae to this and it would stay the same. So we'll have to test that.
Thank you. Ido?
Hi, thanks for the nice talk. So actually I have one kind of trivial question about this graph. So why it seems to be that there are not many supernova around 0.1, like compared. So from a dark energy survey, I understand that you don't measure there, but what about other surveys? So does the ZTF is supposed to have much more supernova in that region? And the second question is about the supernova lensing. I mean, so are you trying to reduce the systematic from supernova lensing, or are you trying to do cosmology with supernova lensing, or both? I mean weak lensing of supernova.
Yeah. The answer is both. So I'll get to that one. The reason that there's a gap here is that we could have combined with Sloan Digital Sky Survey. That's the one that has the most supernovae in this patch. We didn't do that, but we could have and still could. The reason for the dichotomy between low redshift and high redshift is you need very different survey strategies to get high redshift and low redshift ones. So it's just a matter of the fact that supernovae only go off in the galaxy once every few hundred years. And so you need hundreds of galaxies in your field to be able to discover a supernova in a year. And the low redshift ones, you just have to do massive scans of big patches of sky, as opposed to what we did for the high redshift ones, where you can just look along pencil beams and look far away and you get lots of distant ones. And so that's why there's this sort of low redshift, high redshift split. And there are some supernovae in the middle here that we could have added, and we did do tests with them. They didn't actually add much to the constraining power of the entire sample. So it didn't actually change much having a few extra ones in the middle here. So we ended up going with the cleaner sample of not having yet another different sample to calibrate in our data set. Your other question was lensing. So yes, we want to do both. So we're doing testing for the existence of lensing first. So that has only been measured very weakly before, but we expect a skewness to the distribution about the Hubble diagram that's caused because most lines of sight are empty, and a few will be very overdense. So you get a skewness towards having a peak at the faint end and then a tail to high magnification. And how skewed that is tells you how much lensing is along the line of sight. We expect the skew to increase with redshift. And so that's something that we're measuring. So firstly, just the existence of it. Secondly, correlation with line of sight. So existence of skewness is one thing. Correlation with line of sight density. We have excellent maps of the galaxies in these fields now, so we can correlate with the density of galaxies along the line of sight in order to measure that. And then we can also measure cosmology with these things as well, including the density of compact objects along the line of sight as well. So all of the above. It's a really interesting probe that previously has only been, the expected lensing signal is about 1/10 of the intrinsic scatter in type 1a supernovae. So it was only once we had thousands of them at high redshift that we could actually effectively detect this strongly enough.
I mean, okay, it was, I think, a decade ago. The weak lensing was supposed to be like 0.05 times the redshift. But so zero was still consistent, but that was
yeah. So there was some Matt Smith had a paper back in I think 2014 or something along those lines where it measured a correlation with the foreground galaxies, but it was less than 2 sigma at that stage. So with any luck, we'll be able to publish something with a stronger signal than that.
Thanks.
Yeah, and there's been there have been others since as well. So
Thank you so much. Any other questions? No? So let's thank Tamara again.
Thanks very much for having me, everybody. Happy to answer any more questions by email, etc.